Everyone, this is our new platform for our course. I will upload those videos, course videos, to YouTube for you in case we cannot make synchronous lectures due to extreme internet loading. So I will give you the address of those videos in YouTube and you may watch them when you want. Okay, so we will first of all make a summary of the part 5 of the course that we have covered nearly most of it actually. We have just the part of block diagrams has remained actually. We have done all those, but we will just make a review for you and then we will discuss the block diagrams in more detail. Okay, remember the part 1.5 is related with the standard forms of dynamic systems. How to put the dynamic systems in standard forms that we have evaluated previously in the form of differential equations, ordinary differential equations. Remember, the first thing was state variable equations. State variable equations was the generic system dynamics equation for a general system, both linear and nonlinear. And state space was the representation for only linear systems. And if the system is nonlinear and we would like to linearize it for some reason, then we also discussed linearization for that. We mentioned input-output equations for single input, single output systems on which transfer functions are built on. Actually, we find the output divided by input in S domain using Laplace transforms gives us the transfer function. We have made this and we have done some examples. Okay, so let's remember the state variable equations. We define our states. The number of states that we have to define must be equal to the order of the system. So that's the total of order of the order differential equations that represent our system. The system can be a mechanical system, an electrical system, electromechanical system, a hydromechanical system, whatever. Actually, the differential equations of different parts of the system are coupled, so we add up the total order, so we find it as n, so we need n state variables. So we define our state variables by xi's. We have x from 1 through to n, and we have input variables acting on the system. What is that? This is the force or torque, or the voltage supplied to the circuit, or the flow rate supplied to the fluid system, or the heat supplied to a thermal system. That is the input in the system dynamics. So we may have more than one input, so we call them control variables or input variables. So we put our state variable equation in this form. X dot is equal to f of x. Actually, that x is a vector, so we have n number of x dots, we have n number of f's functions, and the functions are maps n plus r variables into one value. Okay. The right-hand side can be linear or nonlinear in state variable equations, but in state space we can only have linear systems that we will discuss in the next section. So that's the state variable equation. Remember, state variable equation example. Remember, we have done it on the board. That's a nonlinear system due to nonlinear stiffness of the spring. And remember, we have defined our state variables as displacement and the velocity of the mass, which is z and z dot, we call them x1 and x2, and we have derived our equation in the form x dot is equal to f of xu. In state space representation, the system that we represent must be linear. Okay, so it has the same approach. We define our state vector for the order of the system. In that case, the differential equation must be linear, remember. And then we define our state space. It's an n-dimensional geometric space that contains the state vector. So you see now the state change is a linear combination of states and the inputs. It's not f of x, that the function now is a linear function. If I have three states and 2 inputs, for instance, these are our equations relating the change in the first state to the other states and inputs. Second state, the change in second state, the change in third state. We can put it in the state space form in matrix vector combination as x dot is equal to a times x plus b times u, where a is a matrix, 3 by 3 matrix, and b matrix is in the form of 3 by 2. That would be the dimension of matrix B. Okay, so that's the output equation. Similar to the state equation, we have our outputs as a linear combination of the states and the inputs. So for our ordinary time invariant linear systems, which are represented by linear order differential equations, the coefficients a, b, c, d are constants. Okay, so we define our state n by 1, input vector r by 1, and output vector m by 1. So that is our system or state matrix A. This is the input matrix. Be careful on the dimensions. Check the dimensions of the matrices when you represent a system in state space. Okay. This is C and this is the D matrix, which we call this is output matrix, and D matrix is the direct link matrix, or we also call it direct feed-through matrix. As I said, the dimensions of the matrix must be consistent. Check the number of inputs, number of outputs, and your system order so that the matrices are consistent with the vector dimensions. Okay, so we put the system in this form. That's the state equation. That x dot is a vector, ax plus bu, y is equal to cx plus du. We have shown the mass spring damper example on the board. Remember, x dot is equal to 0, 1 minus k over m minus b over m times x plus 0, 1 over m times u. U was the force applied to the mass spring damper system. Okay, we have also done this example. This is the DC motor example. In state space representation we can show it because you see it's a linear differential equation with constant coefficients, so we can put it directly in state space representation. We need 3 state variables because that's a second order, that's a first order equation. They are coupled. In mechanical equation we have the electrical variable current, and in the electrical equation we have the mechanical variable angular velocity of the rotor. So they must be solved together. That's a third order system. So n is equal to 3. So we need 3 state variables. We define our state variables as current, angular position, and angular velocity. And we define our input vector. This is the voltage applied to the rotor coils to the armature. And this is the torque load, where the motor is supplying the torque. And assume that the output, actually not assume, it is given in the example. A tachometer is used to measure angular velocity, theta dot, and an ammeter is used to measure the current. So my output is theta dot and I. Actually, theta dot is the third state variable and the current is the first state variable. So I can write it like this. And furthermore, I can write this in the form y is equal to c times x, because that's the third state, that's the first state. So I can easily see that my C matrix will be equal to 0, 0, 1, 1, 0, 0. Okay, we will see that later on. Okay, we derive the derivation on the board. We have done this, remember, in the class. So that was the matrix A, B, C, and D. Check and verify the dimensions, as I said, the matrix vector multiplication. As this is 3 by 3, this vector must have 3 rows. This is usually 3 by 2, so this vector should have 2 rows. Okay. Linearization, remember, was an important topic that we have discussed. It's based on the Taylor series expansion, and a linearized model is only valid around the point that we linearize it. So it's reasonable and accurate representation as long as the dynamic variables do not deviate too far from the operating point. Okay, so we have shown the 3 basic steps in linearization. Choose or solve for the nominal operating point to linearize the system about. That was the first thing. So where do we linearize the system? Redefine the governing equations in terms of nominal variables and perturbation variables. Remember, what was perturbation? It's delta. We show it with del x. Del x is equal to x minus x star. That x star is the nominal operating point that we linearize the system, and x is the state of the system, and del x is the difference from the nominal operating point. And similarly, we have del u defined similarly. Expand all nonlinear terms in Taylor series and retain only the first term in the Taylor series. Okay, the first example is a static system, not a dynamic system. Remember, a static system is represented by an algebraic equation, not a differential equation. For example, the flow versus pressure drop through a valve. That was the equation, remember, for a turbulent flow. For laminar flow, it was linear. Q is equal to kT times pressure, remember. But most of the flow conditions in valves are turbulent. So P versus Q curve is that blue curve. We would like to approximate this with a linear model. So that linear model will be valid around the operating point, which is P star, which is at 400 kilopascals, and the flow rate corresponding to that. I can find the flow rate corresponding to that from that equation. Okay, so we will continue the course on the second video. Bye for now.